Hi everyone, welcome to Chemistry and Society. This is just an introduction section, and just to introduce you to what this course is about and hopefully get your appetite whet on terms of what we're going to be studying this semester. The objective of this course is for first of all, for non-science majors. The course emphasizes conceptual topics in chemistry and scientific thinking. You will learn to understand how society uses chemistry-based technology and how to analyze current trends or news involving chemistry. Topics include a basic understanding of matter and energy, physical and chemical change, the atom, nuclear chemistry, bonding, acids and bases, organic chemistry, and biochemistry. Current issues in environmental chemistry such as energy resources, air, water pollution are explored also in this course. Students discuss the effect and controversy surrounding the use of the different forms of energy. This course will hopefully make you knowledgeable in these topics and give you some wisdom as far as making some decisions involving your environment and some of the items that will be covered here. So why are you taking this course? Most of you are going to say it's a required for your majors. I doubt if any of you are chemistry majors, but if you do decide to go into chemistry, then there's a lot of opportunities out there. But in general, in science, if you go into the science field, there's many career options that can be had, and here are just a few that you see right here. If you take this course, then you're really studying science. Chemistry is a branch of science, and science in Latin is knowledge. And knowledge in science is more than a collective collection of facts. It involves comprehension, correlation, and an ability to explain established facts, usually in terms of a physical cause or for an observation. In fact, Carl Sagan said it best: science is more than a body of knowledge. It is a way of thinking, a way of skeptically interrogating the universe. Stephen Hawking said that scientists have become the bearer of the torch of discovery in our quest for knowledge. Science really is about the understanding of the universe. Science encompasses the universe. A better understanding of our universe leads to the improvement to our quality of life. And in our universe, we think of it as both having form or matter and energy. And these two are related by Einstein's famous equation, E equals mc squared. Together, they form our physical universe. Now, science and technology share a relationship. And this is just an example in this slide of how science has advanced technology. Consider a little bit more than 100 years ago. If a child has an infection, then the sickness can easily spread from, say, that child's ear to their entire body. Their skin is scarlet, and the child is generally in great pain. For those of you who have children out there, you know that it's basically streptococcus. Back in 1896, the doctors would simply apply tincture of iodine and expect the best. Most children did not live past 4 years old. A little bit more than, say, 20 years ago, a child would go to the doctor. The pediatrician would diagnose the sickness as streptococcus infection, give them antibiotics, amoxicillin. I think that's still being given out today. It has a pink color to it, and it tastes sweet, and children generally take it, and within a few days the fever and pain is gone. Imagine 20 years from now, in fact 10 years from now to be exact, you can think of a a kid who has had their genes altered so that they do not get some of these genetic disease, and that their immune system can kill the bacteria and viral inspection. That is the world that we are going into. That's pretty amazing. Science is responsible for the quality of life and us advancing in years. Science itself can't cause change. Likewise, technology cannot happen without science. But there is a symbiotic relationship. And here in this particular slide, you see how some of that discovery, like the discovery of the atom and its understanding, led to both medicinal purpose, like the MRI, imaging machine, and military applications, the atomic bomb. How is science different from the technology? Basic science, the accumulation of knowledge about the universe, requires adhering to logical guidelines. In fact, that's what you guys will be doing in this course. You will be using the scientific method. Technology is defined as using scientific knowledge to manipulate nature. To make science translate to technology, science must be great solving problem solver, because they need to take the fundamentals of science and apply it to their needs. Some examples is how we use chemical reactions to operate our cell phones or these hybrid cars. Let's just take a look at some incubation period for some discoveries, and then the technology that preceded that. Take, for example, antibiotics. It was first conceived in 1910. The first application happened in 1940, which was really important because that was right before World War II, and a lot of lives were saved because of antibiotics. Heart pacemaker, that was conceived back in 1928, and the first heart pacemaker was actually built in 1960. Nylons, that was conceived in 1927, and then we started using nylons for nylon stockings and parachute in 1939. Xerox, what would we do without copying machines? Well, that was conceived in 1935. The first copier was made in 1950. And photography, that was conceived in 1782, and the first camera was invented in 1838. So you can see here that the invention that arises from the scientific discovery can have variable incubation period. Today we see technological revolutions happening everywhere in our daily lives. What do you think are the current biggest technological revolutions that is happening? 20 years ago, it was the computer chip and recombinant DNA. The computer chip allows us to have our smartphone now, and where would we be without our smartphones? And recombinant DNA, well, we've mapped out the genome for the human race, and now we're trying to fight diseases using that technology. Technology doesn't come without a price, however. There are risks and benefits to a technological society. There are many benefits, such as we can have more crops, we can go faster in our vehicle, we can travel space, but there's also a downside. Pesticide to improve crops? Well, there was a deadly accident in Bhopal, India that killed 2,000 when that pesticide escaped the manufacturing plant. Nuclear fission? Well, you guys have heard about the Chernobyl nuclear power plant, and then more recently, the Japan nuclear meltdown. And so, again, these are technological disasters. Space travel, the Challenger disaster, that's sort of dated. and automobiles, leaded fuel, that sort of data, but those were real problems back in the days. So what are acceptable risks? Society tend to judge involuntary exposure to activities and technological riskier than voluntary exposures. So nuclear power plants are considered dangerous, but if you use them and you take advantage of them, then they're acceptable, like in Europe. Um, Cigarettes, we try not to deal with secondhand smoke, and yet there's still a lot of people who can't break the habit. Weekends, we drink a lot of our alcoholic beverage for a good time, and yet when we get behind the wheels, that can lead to disaster. And medicinal marijuana, that's been in the news lately. Um, that's Voters are now um, deciding whether they will have medicinal marijuana or even marijuana legalized in their state. So, what exactly are acceptable risks? This is an interesting article because chemistry seems to have a good connotation. Chemistry is responsible for good living, clean air. If you remove the contaminants, chemistry is responsible for our computers, our improvement in our quality of life. But chemicals, well, they don't have such a good connotation. Um, Chemicals tend to have a negative image, and yet an understanding of what chemicals are will have you realize that not all chemicals are bad. In fact, this article, you should download this article and read it, because when dioxin was first studied, the EPA called it the deadliest chemical known to humans. And by 1991, the federal government had to retract that because dioxin really wasn't as harmless as people say. So there's a lot of examples through history about this where we jump the gun and say that it's a really deadly chemical. Everything's deadly. It depends on the quantity. The dosage makes the poison. So please read this article and get a better idea of what exactly why things are classified as dangerous and why things are okay. Everything is dangerous, like I said, depending on the quantity. The bottom line, there is no absolute answer to the question how safe is safe. It is difficult to determine the risk. To assess risk, knowledge of toxicity and exposure is required. Exposure. This is easily measured and is based on the amount of time exposed and quantity of the material. Toxicity, however, is difficult to measure. How can toxicity be determined? Do we use human population? That's unethical. Do we use statistical analysis? That's vague. Do we do animal studies? Well, animal rights will get at you. So again, how safe is safe? It's very difficult to quantify. We as informed consumers have a responsibility to be educated so we can weigh the risks and benefits, and hopefully after this class you will be able to understand the science behind certain consumer goods so that you can make sound judgment when you read or you encounter some of these issues that we are encountering in today's society. So let me wrap up by telling you that science is an amazing subject, but science, chemistry, is just one of many subjects in science. If you take math, math is considered the language of science. Biology is the science of the living. Physics, science of the way things work. And chemistry is the science of the building block of matter. I like to call chemistry Lego science because if you think of the atoms as Lego bricks, and you've been to Disney Legoland and you've seen what they've built with these Lego blocks, well, with atoms we build the universe. So chemistry is often called the central science. What is matter? Anything that contains substance, occupies space, and has mass. Mass is a measure of quantity. Don't confuse mass with weight. Weight is some force due to gravity. Since matter is everywhere, consider chemistry to be everywhere. Here are just a few examples of certain items and the size of matter. When we talk about the atomic scale, we're looking at 10 to the minus 12 meters. That's in the realm of nanometers when we're looking at subatomic particle. When we're talking about cells and viruses and DNA, we're looking at micrometers. That's the microscopic world. Our world, the macroscopic world, is about meters, centimeters to meters. That's the length of the things that we see. And then as we expand that, we hit the cosmic scale, and that's the size of sun, galaxies, and comets. Let me just show you a video real quick so you can see the scale that I'm talking about. So this particular video is right here. Let's take a look at this. Let's do this. So what we're doing here is we're decreasing in size. All the way. Well, actually, we're increasing in size. We went from the atomic scale to the macroscopic scale to the cosmic scale. Go to this website if you want to see this in slow motion. It's a pretty interesting website, and it's expanding in powers of 10. Let's decrease. And you can see that we are now going from the Milky Way galaxy down to our solar system, and then down to planet Earth, and then down to the state of Florida, and then to Tallahassee, to a park in Tallahassee, to a tree in Tallahassee, to a leaf, to a cell, down to the DNA, down to the atoms, beyond the electron cloud, down to the protons and the nucleus of the atom. So that is an example of the different scales of matter, and I hope you learn a lot.